This is the second set of lecture on inferential statistics. We'll talk about different tests used to compare means in a different design of experiment or studies. So there are three different kinds of t-test: one sample t-test, test, matched paired samples t-test, and one way ANOVA or ANCOVA, analysis of covariance. When you have a multiple independent variables, uh, you need to understand how two-way or three-way ANOVAs work. So these are the kind of things that we will talk about. One of the things that researchers need to decide is what kind of analysis can be used uh, for data analysis. So I would like you to kind of recall uh, the flow chart or decision chart that we talked about when at the end of the semester in statistics lecture. So I'm not gonna going to cover that in that much details, but these are the three different kinds of factors or attributes of your study design or the data that needs to be considered when deciding which test to be performed. Okay, number one is how many sets of means needs to be compared. If two, then it's basically t-test. If more than two, then you need to use ANOVA. Even if it's actually two means are compared, you can also use ANOVA. Okay. And number two is what kind of comparison between two and the two means. So for example, sometimes two sets of means that you have can be unrelated. In that case, it's an independent groups. If it's an independent groups, then it's either independent samples t-test or between subjects and over in case that you have three or more groups. On the other hand, if these two or three means that you're trying to compare are related, such as repeated measure designs, then it's going to be repeated paired samples t-test or repeated measure ANOVA or mixed factor ANOVA. Okay? And then finally, you also need to understand how many factors do you have. If there is one factor, which means one independent variable, then either t-test or one-way ANOVA is appropriate. On the other hand, if you have two or more independent variables, in that case, you have to use multifactorial ANOVA. So extending the discussion from previous slide, one way to look at or decide the data structure is by looking at the structure of the database. So I have here two different kinds of structure of the database. The first one, the left side is when basically your sample or structure of your study is actually based on independent groups comparison. So here we have uh, one, two, three, four, five, six. Six people, and six people have different scores, such as one first person has having 10, second person having 8, and so on. So, and then when you look at the first column, which is basically the variable to designate group, it belongs to either group 1 or group 2. So this means it's actually all the people are randomly assigned to either group 1 or group 2. This means it's an independent groups design. On the other hand, when you look at the right side, you have two sets of data belonging to the column 1 and column 2. That's designated as a condition 1 score and condition 2 scores. So this means each individual person has two sets of data. This signifies this is a repeated measure designs, therefore it can be paired. The comparison is for the first person 7 to 10, second person 7 to 10, the third person 8 to 8. So in this case, this is a paired samples t-test because it's a repeated measure design.
So we'll talk about between subjects two-way analysis of variance. So first I want you to look at the very first table, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 people. So look at these 14 people's data. Okay, and so that's the dependent variable, or the score on the dependent variables is the basketball shoot. How many of them actually out of 10 made it to the basket is on the last column. That's third column. The first column is the factor 1, which is the assignment of the people into the condition of higher arousal versus lower arousal. Half of them are in lower arousal condition the first half, and then half of them are in high arousal condition. And then the factor 2 is the training assignment. So there are some of these people who's the low training, and then some of these people are high training conditions. And now I want you to look at the pairing, the combination of these two columns, first two columns. So the first person number one is low. So that means low training condition and low arousal condition. But look at number 5 person, LH. So that means low arousal and high training. Then look at 1, 2, 3, 4, 5, 6, 7, 8. Eighth person is HL. So that means high arousal but the low training. Then the last person, for example, is high and high. That means high arousal and low training condition. So these actually forms actually 4 different kinds of condition: low training, low arousal; high training, low arousal; low training, high arousal; and high training, high arousal. Then, so the second table here, you can see these are the average of these people who is in each of the 4 conditions. Okay, so based on this, I'm not going to talk about the actual statistical procedure. 3 hypotheses can be tested. The first is the main effect of arousal. The main effect of arousal means if there is any significant effect of arousal alone when you ignore the effect of the training condition. So you are treating this as almost like a t-test, comparing a high arousal condition and low arousal condition, ignoring training condition. The second hypothesis to be tested is the main effect of training, which is basically the difference between low training and high training, treating as if this is a t-test between low training condition and high training condition. Then the third hypothesis to be tested is an interaction between arousal and training. This hypothesis tests whether or not the effect of the training conditions, such as low training versus high training, is dependent on the levels of arousal, or the effect of the arousal is dependent on the levels of training condition. Okay, so we already talked about how you look at the factorial design study, so we are not going to talk about it in here, and just recapping what we already discussed a while ago.
That you have a good understanding by now about what analysis to use and the kind of structure of the data, which help you to decide which types of analysis to use. Then we're going to kind of step back, and I would like you to think about what sort of mental operations that we are doing when you perform uh, inferential statistics. Okay, so the goal of inferential statistics is to figure out about the population, not about sample. But all you have is a set of samples. That's why you try to infer the nature of the population based on the characteristics of sample. So you use sample statistic and then to make an inferences about population means or population parameters. So in comparing means, what you're doing is you have observed means, which is a sample means. And you compare the sample means, and then you try to make an inferences about the difference in population means. Therefore, you begin by assuming that two population means are the same because you don't know. So that's the least problematic assumption. And then you look at the difference in observed mean. And then you are going to think, if two population means are assumed to be the same, is the data that you have actually, that's an observed mean difference, is likely to occur or doesn't likely to occur? So if the observed mean difference is actually unlikely to occur, given the belief that two population means are the same, now the data allows you or forces you to change your mind. And therefore, you are going to reject the null hypothesis and change the belief that two population means are now the different, because the observed sample mean indicate otherwise. In performing the inferential statistics that briefly described in the previous slide, uh, the actual decision that you make on the population means based on the sample mean, observed sample mean, is not absolute or definite categorical decision. It's a probabilistic decision. Therefore, we need to rely on something called p-value. P-value is the probability of obtaining a particular test statistic, such as t-test, t-value, or f-test, f-value. Uh, and so this requires you need to understand the actual meaning of the p-value. So the meaning of the p-value is based on the assumption that, first, the null hypothesis is actually true. So this means population means are actually the same. So the p-value, however, is based on the sample statistics. That means you remember that the p-value associated with t-test is computed by uh, observed mean difference divided by standard error of the mean. So therefore, the larger the mean difference in observed mean, the bigger the t-value. And then the p-value is actually very small when t-value is large. This is because if you assume that two population means are the same, probability of obtaining such a large t-value is very small. And that's the meaning of the p-value. And when the p-value gets too small, such as 0.01 or smaller, this means if you assume that two population means are the same, this type of large t-value, which puts the probability is very low, like 1 in 100 times, should not occur. Therefore, it allows you to reject the null and change your hypothesis and accept the alternative hypothesis, which says two population means must be different. So by now, you should be aware that statistical inference, which takes the form of hypothesis testing, the goal is to make inferences about uh, the difference of population means, whether or not two population means or three population means are different. But in doing so, you use sample statistics. That means two or more sample means. Okay, and then the second things that you need to be aware of is your decision on the difference on the population mean is a probabilistic because we are relying on p-value. Remember that our reasoning goes like this. If you assume that two population means are the same, this kind of mean difference should not occur. That means very low probability of occurrence. Now that occurred. Therefore, we have to change our belief hypothesis that two population means are likely to be different. Note here, it's likely to be different. You don't know whether it's actually different. Therefore, your decision is probabilistic. Therefore, it is possible that you're committing errors. So there are two different kinds of errors possible in this process. So that's what we are going to talk about. So there are two different kinds of errors that's possible in statistical decision making. So type 1 error is actually you declaring two population means are the same, even though in fact two population means are actually the same. So you shouldn't have rejected the null hypothesis, even though you actually rejected it. That's the type 1 error. So the other way to say it is a false positive. Positively claiming that two population means are the same, even though it's not the same. The opposite is a type 2 error. You actually declare at the end of the analysis two population means are the same. However, in reality, two population means are actually different. So you should have rejected, but you actually didn't reject the null hypothesis. That's the type 2 error. The other way to say it is a false negative or miss. Another way of talking or actually understanding type 1 and type 2 error. We use 2 by 2 table here. So the column represents actual truth about the population that you never know, but we assume that it's categorical. Either population means are different or population means are not different. And then the row, that's the top and bottom, represents two different kinds of categorical decisions that you actually make. Now, at the top is rejecting the null hypothesis, declaring that two population means are different. And the bottom is keeping the null hypothesis. That means declaring two population means are actually the same. So this produces when population means are actually different, and then you collectively reject the null hypothesis, and the population means are not different, and you collectively keep the null hypothesis. That's correct. However, type 1 error happens when the population means are actually not different, but you reject the null. Type 2 error happens when the population means are actually different, but you fail to reject the null hypothesis. We talked about various factors such as effect size, sample size that affect the type 1 and type 2 error. But here, I'm hoping that you still remember that. And so because of the limited time, we focus on here the alpha level that's going to determine the risk of type 1 and type 2 error. An example in which that you decide to use very small alpha, such as alpha as a p-value of 0.001. So this means you're making it very difficult to reject the null hypothesis because your decision threshold is very high. Because unless you get really extreme t-value or f-value, you are not going to reject the null hypothesis. This means because the area of rejection is very small, therefore type 1 error gets very small as well. But however, this means type 2 error increases because you have a large chance of not rejecting the null hypothesis. The opposite from the previous slide. So now you are using the alpha level at the P5. This makes it very easy to reject the null hypothesis because you have a large rejection area. So in this case, you have a small chance of type 2 error because you are very likely to reject the null hypothesis. When you reject the null, you don't have a false negative. You don't miss. The likelihood of missing is actually small, so therefore type 2 error. However, because you have a large rejection error, it's possible that you falsely reject the null hypothesis. So therefore, you have a large chance of type 1 error. Making a decision of either using small alpha or large alpha, we need to be concerned about which of type 1 and type 2 error is more serious. So implication of type 1 error. Type 1 error is serious when convicting a person of a crime when in fact the person is innocent, but also not serious in another case, such as erroneously diagnosing a patient with cancer when they actually don't have it. Because the reason is, if you suspect somebody having cancer. You're going to have a follow-up test. And if it's a false, it's going to be discovered as a false, identified as a false in the follow-up test. So there isn't that much bad consequence. Now, what about a consequence of type 2 error? Type 2 error is very serious in a sense failing to detect cancer when a person actually does have cancer. Okay, because if you miss the cancer in the first screening, then there is no follow-up analysis, then it's not going to be detected. It's going to have a large, significant, serious consequence. But it may not be serious in a different sense, like letting claimant go due to lack of sufficient evidence. Right? So based on these, we have to come up with some kind of uh, systematic pathway of making decision.
So overall, type 1 and type 2 errors have different consequences and seriousness depending on different kinds of situations. And also important to note is when one try to decrease type 1 error, it tend to increase type 2 error. And if one try to decrease type 2 error, it tend to increase type 1 error. So they are in trade-off relations. So are there any ways or rules of thumb that help you decide what kind of alpha level or one choose to uh, reduce type 1 or type 2 error? That's a difficult question, but here is the one guideline that I would suggest. Okay? Generally, at the early stages of research, type 2 error is more serious. Uh, the reason? Because sometimes what you try to detect is the very small effect. And you do not want to kill your research uh, prematurely by failing to detect the effect which is small to begin with until you come up with a better method to detect uh, the effect more reliably. So at the early stages, you want to decrease type 2 error as opposed to type 1 error. Uh, and so let's look at the other example. So for example, we can think about the detecting, diagnosing breast cancer. The false positive, that means believing that there is a possible cancer in the early stages of breast cancer screening is uh, not as problematic as missing it, because even if you falsely detect it, the more repeated testing is going to eventually tell you that it was a false positive. But if you miss it, that's much more serious because there is no subsequent testing. So you want to minimize the type 2 error at the beginning. So the larger alpha level should be preferred at the beginning of the research. On the other hand, at the later, in particular, the final stage of research where you actually make an important decision of, say, that you're going to start producing the medicine, or you actually want to have the actual surgery, you want to minimize type 1 error because you really want to make sure what you found is real. Imagine that you are trying to remove the breast cancer and then find it's not the breast cancer, so it's a serious. Or imagine that you're trying to sell the medicine which actually doesn't have a real effect. So therefore, in the final stages of the research, you really absolutely make sure the effect that you detected is real. So therefore, you need to reduce the type 1 error. So it's more advisable to use smaller alpha to raise the threshold of rejecting the null hypothesis at the later stage of the research.
Okay, changing the topic now. So sometimes you have three different kinds of groups or conditions And then you have a choice of doing either three pairwise t-test or doing just one way and over. And I hope you remember that the better is to conduct just one way and over. Why conducting three pairwise comparison is not a good idea. Uh, this thinking involves the accumulation of type 1 error. Okay. So if you perform three t-tests for the same data, basically you are capitalizing on the chance. The reason why is because each test, statistical testing, involves possibility of type 1 error. And given that each test runs the risk of type 1 error, and then a type of the risk of type 1 error that you're accepting when you're using alpha equal 0.05, that means 5% chance. This is because adapting alpha equal p level of 0.05 means even if null hypothesis is true, there is a 5% chance of finding the observed sample mean difference as large as what you actually observe. So therefore, it's a 5%. So if you run three tests, it's a 5% plus 5% plus 5%. So among three tests, there is actually at least 15% chance of rejecting the null hypothesis by just false positive pure accident, because it's test A or test B or test C. So therefore, now you are changing the kind of decision criteria of statistical test if you do so. This is the reason why you shouldn't run multiple tests for the same data.
Okay, so in the previous several slides before, we talked about and emphasized that even though researchers choose alpha, which is a threshold level, to influence the probability of risk of type 1 or type 2 error, you cannot reduce both using choosing alpha. If you increase type 1, if you decrease type 1 error, you increase type 2 error. If you decrease type 2 error, you increase type 1 error. So the alpha, you can't play too much with that. But there is another way to reduce type 1 and type 2 error. And in this case, we think about the possibility of reducing both type 1 and type 2 errors. There is only one way you can reduce both type 1 and type 2 error. What is it?
By enlarging your sample size.
Yes, that's right. So let's kind of think about why that decreases both type 1 and type 2 error. Okay. A large sample size decreases first type 2 error because it increases the chance of rejecting the null hypothesis. Why it increases the chance of rejecting the null hypothesis? Because when you have a larger sample size, standard error of the mean tend to get smaller because of this formula. Standard error of the mean is computed by standard deviation divided by square root of n.
Right.
Therefore, when the sample size gets larger, standard error of mean gets smaller, and when the standard error of means gets smaller, the observed t tend to get bigger. Therefore, you tend to reject the null hypothesis. So the formula has a built-in mechanisms to increase the rejection when the sample size is large.
Right.
So that's the type 2 error decrease due to larger sample size. Now, when you look at the actual sample size, besides the formula, when the sample size is larger, the statistics, that means the observed statistic, becomes more consistent. Eventually it becomes the same when you reach the infinite sample size.
Right.
Therefore, it also decreases type 1 error because it becomes much more stable and consistent. So in this way, the larger sample size is the single most important thing. And then, so this means, given so also this is related to representative sample. It's extremely difficult to have a representative sample with a sample size of 2.
Right.
Right? But if you have infinite sample size, it always becomes representative sample. So therefore, the larger the sample size, it gets closer to representative sample even if you don't pay attention to that. So that's why the large sample is extremely important.
Right.
We try to sum up. Okay, so what's the point? What's a significant result means? So typically we use the results as significant. Significant results means that observed mean difference is significantly large relative to estimated sampling error. Therefore, your decision is likely to be reliable. This means it's likely to reflect the actual difference in population. Therefore, you are more likely to observe this on a consistent basis. Note that p smaller than 0.001 means there is very small chance, smaller than 0.1% chance that these results happen when the actual population means are the same. Therefore, it's very likely population means are actually different. That's what this means. It is very important you just understand not only interpreting the meaning of significant results, but I would also like you to understand the meaning of non-significant result. It's very precise meaning. Non-significant results means multiple possibilities exist. Number one, as indicated by the analysis, it is possible that actually there is no difference between two population means. But it also could be, number one, it could be due to type 2 error caused by small effect size. The effect size that you're trying to detect, which is the difference in the population mean relative to variability, such as standard deviation, is very small. The number two, type 2 error caused by small sample size. Your analysis or your actual setup was not sensitive enough to get basically the results, the mean difference that you set out to actually detect. Talk about non-significant results and its use in a little more extensive way. Okay? Non-significant results as a result of statistical testing means your data is inconclusive in its power to change the existing hypothesis. Therefore, a professional journal is not interested in publishing the results with non-significant finding with the non-significant results. That's the usual case. However, there are some exceptions. Sometimes non-significant results provide new information such that it's going to change the existing idea. That happens when you fail to replicate the existing finding, which is sort of accepted as true as a consensus. So the reason why in that situation, the journal article published the non-significant results is it changes the existing opinion. Okay, so for example, let's think that you have situations where the effect of this particular medicine or clinical intervention is accepted as effective in improving the people's health or mental health. Now you conducted the same study to replicate it with a larger sample size. The previous study used only the sample of 100. Now your study used the sample of 500. Okay, and then you fail to reject the null hypothesis. This means even though the consensus up to that point is the medicine is actually effective, now your study with a larger sample size shows that it's not effective. So therefore, it provides new information that forces people to reconsider and change the status of that idea from conclusively positive to inconclusive, which is informative. So in that situations, non-significant results are very informative, and therefore it's actually tend to be published.